I see. Ah, I see.
Does he know you? Maybe he's one of your former students.
I don't know. I used to know like the guy who was the mascot for the baseball team in town. What's it called? The Hillcats. That passed to a couple different math majors from year to year.
Really?
Yeah. So I never really been to a Hillcats game, but I knew the mascot. So anyway, I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for these students, this class. Just pray that you just be with us today. Help us to glorify you what we do, Lord. In your name I pray, Lord Jesus. Amen.
Amen.
All right, let me begin with a proof, a proof of something here. So suppose that U and W are positive. All right, and let A also be a positive number. All right, so check this out. If I have A to the log base A of U plus the log base A of W, what would that be equal to? Say the third.
So,
Yeah.
Cool.
so A times log A.
So yeah, this would be A to the log base A of U times A to the log base A of W, right? And how do I know that this is true? What am I using? The law of exponents, right? If we have the exponent of the sum, it's the product of the exponentials like this, right? So I'm just using like A to the S plus T. You guys remember this, right? A to the S plus T is equal to A to the S times A to the T, right? That law. So I'm just using that here, right? But what is, by definition of the exponential, this is what? This is equal to U times W, right? Everybody with me?
I'm with you.
Okay, so
Excuse me, might I borrow someone's pen for a minute?
Sure.
Thanks.
so look at this then. We've got this right here is equal to this right there, right? So take the log base A of both sides, what do you get?
Log A U W A L.
All right. But how does the left-hand side simplify? Log base A of that, by definition, inverse function, it is log base A of U plus log base A of W equals to log base A of UW. So there you go. That's one of the properties of the logarithm that I claimed was true last time, right? And as I said, it's a consequence of the corresponding law of exponents, all right? So there's the proof of one of our laws of exponents. I'll show you the other one. All right, so my second proof for you guys is if we look at U we can write U equals to A to the log base A of U, right? I mean, this is an identity. I can do that, right? Then what happens when I raise both sides to the p power? Like what's U to the power p is equal to A log base A of U all to the power p. How does that work? Do you remember the other law of exponents? A to the S, parentheses, exponentiated to the t power is a to the st. I'll write it out, Michael. Just a second here. So what
Just try to get everything.
very good. So you guys remember this one? A to the s raised to the t power is a to the st, right? So using that here, thinking of s being my log base a of u and my t being p, this gives us a times p log base a of u. But then what I can do is I take log base a of both sides. See? So I get log base a of u to the p equals to log base a of a to the p log base a of u. But the what's the word here? The right-hand side, it simplifies, right? The right-hand side simplifies simply to p log base a
L
of u. In other words, this proves that log base a of u to the power p is p times the log base a of u. So that's how we can derive the properties of logs from the properties of exponential, okay? Basically, you just play this game with converting something to an exponential by using this little trick right here, yeah? So the other thing I should tell you guys about is the change of base formula. Well, I guess there's we had one other property, right? What was that? Yeah? Log base. So log base a of u over w, okay? That was the other one.
Property.
So Michael, up here, buddy. Log base a of u over w, that was the other one.
Exponential.
Right? So then what? This we could write as a product, right? This is log base a of what? U times what?
W.
Not w, but
Log
w to the minus 1, right?
U.
Do we agree? So then I can use the property that I proved at the start of class to write that as a sum of the logs. See? This is equal to log base a of u plus the log base a of w to the minus 1 power. But then we can use the power property of the natural log to do what? To bring out the minus 1. See? And so this is equal to log base a of u minus log base a of w. And so there's the other log law. So I'm just going to write them over here for reference. So with the three log laws that we like to use, log base a of u to the power p is p log base a of u. Log base a of u over w is log base a of u minus log base a of w. Those are the three major laws of logarithms. All right? Any questions about any particular homework or anything? Okay.
Oh, actually, I do have a question.
All right.
So, it concerns about problem number 107. Solve 4 to the x plus 2 to the x minus 12 equals 0.
Oh, this is a tricky one.
I know I've gotten ahead, but I need help with it anyway.
Okay, so
Thank you.
if you guys don't mind me doing a problem that's slightly ahead of schedule, right? Nobody? Yeah. All right, so I will change this problem for you, Michael, a little bit and do 9 to the x plus 3 to the x minus 12 equal to 0. Maybe we can solve this one. So this is like problem 107, but I changed it just a little bit, okay? So any ideas how we'd solve it? This one's different than anything we've done so far, guys, with this part of the material. All right? Any ideas? Anybody?
Well, based on my definition.
Now, Michael, I told you earlier today that we can solve most problems by taking the natural log.
Natural log of both sides.
Now here, that would be a bad idea. What's the natural log of 0?
1.
Oh, no, no. Natural log of 0
0.
is not 0. Natural log of 0.
1.
The natural, get your calculator out. Try natural log of 0. See what happens. Oops.
It says domain error.
Domain error. While you guys got your calculators out, try natural log of -1. See what happens.
Nothing.
Yeah, again, domain error, right? So natural log, we can only take the natural log, or really any log, of a positive quantity. All right, so something like this, like natural log, won't help me directly at least. All right, just saying. So this requires some other kind of scheme. And so basically this is the trick, is to notice that 9 is equal to 3 squared, right? So 9 to the x is equal to 3 squared to the x, right? Which is equal to 3 to the x squared. So what is this then? Let's rewrite this. The equation we have is 3 to the x squared plus 3 to the x minus 12 equals to 0. Now that I've written it this way, anybody give me a piece of advice? What should I do? Make a substitution maybe? What should I try substituting? How about y equals something? Y equals what?
Y equals 3 to the x.
That sounds like a plan. Y equals 3 to the x is a good idea.
Y squared plus y minus 12 equals 0.
Now can we solve this? Can you factor that?
No.
I hear one vote for no, one vote for yes. Somebody's got to be right. You're like, whether or not I can factor, it's a deeply personal question. That depends on, you know, how I'm feeling in the given day. Do I have the motivation to factor?
So,
Do I remember how to factor?
take the 12.
Take 12.
Make it 12.
12 is 1 times 12. It's 2 times 6. It's 3 times 4.
It's 5 plus 4 plus 5
I like 3 and 4 because we've got a coefficient of 1, right? So, and we want the 4 to win because we want a plus 1. So what we're going to do, y plus 4 times y minus 3. So y plus 4 times y minus 3 is equal to 0. So what does this tell us? So we've got y equals to minus 4, or we've got y is equal to 3. All right? What was y? Is y the answer? No, right? We need to find x. So what we have now, we have 3 to the power x is equal to minus 4, or we have 3 to the power x is equal to 3. So,
Oh,
yeah.
1. X equals 1.
For which one?
9
Oh, this one?
power of 1.
Yeah, this, you're like x equals to 1 here?
Yes.
That's right, because 3 is 3 to the 1. So by the 1-to-1 property, we have the solution x equals to 1. How about the 3 to the x equals to minus 4? Is this possible? Remember what the graph of 3 to the x looks like? It looks like that, right? So the range of 3 to the x is what? Remember, it's 0 to infinity? You cannot have 3 to the x equals to minus 4. It's impossible. So the answer to that one is no solution. Right?
Oh, no solution.
No solution there. So even though we get 2 values for y, only one of those actually produces a solution to our original problem. Does that make sense to you guys?
Uh-huh.
Okay. So there are problems like this. Now, the other thing I should talk to you guys about, if I can find a marker that I like, is change of base.
Change of base formula.
Yeah, let's talk about the change of base formula. All right. So the change of base formula says that log base a of x is equal to log base b of x divided by log base b of a. Or if you like, log base a of x is equal to natural log of x divided by the natural log of a. There's a specific, I mean, we can use the natural log to change the base if you like. So let's try this out. Let's see if we can use the change of base formula to calculate you know, a particular value here. So example 2, let's use the change of base formula. All right. Let's try to calculate the log base 3 of, let's say, 7. Well, I can do that with a change of base formula. That's going to be the natural log of 7 divided by the natural log of 3. So this is important because some of you might have a calculator that doesn't have log base 3 on it, right? So if your calculator doesn't have log base 3, it's okay because you can still calculate the natural log. So I've got natural log of 7 is approximately 1.94591. Natural log of 3 is 1.09861. And so to a good approximation, we have, what's the decimal of this? I get 1.7712. So there you go. We can find log in another base by using the natural log function and the change of base formula. Like, this is important to me because on my calculator, which I love very much, I just can't find the log base 3 button. All right? It's just not on there. I mean, I've been told that it's in there somewhere, but I got to get to a menu and then go to a thing, or it's just here and I'm not looking at it. Maybe it's here. Oh, there it is. Log. Actually, I do have log. I wanted log base 3 of 7. So my calculator does have it, actually, truth be told. So if I do that directly in my calculator, it gives me 1.7712. 7, 1, 2, 4, 3, 7, 4, 9. So, hooray. That agrees. But maybe your calculator doesn't have a log base whatever button. I don't know. Any questions?
Well, actually,
Yeah.
I do have.
You have more
would you like
questions?
to let someone else go or me?
Well, if no one else has a question, I guess it's going to be you.
Anyone else have a question? All right. Well, I would like to solve solve the natural log of x minus 1 plus natural log of x plus 1 equals the natural log of 3.
Okay, so example 3.
Oh, thank you.
So you, I'm trying not to solve your homework directly. So can I just see it for a second? I'll make a similar problem.
Similar.
Yeah, because I know you don't like me to solve the problem. Let's see here. And that would offend everyone else as well if I was to actually solve the given problem.
Just trying to work ahead of
People
everyone else.
would be very annoyed if I was to solve the actual given problem, right?
So tragic.
No, it would be, I think it would be devastating.
You'd be devastated. All right, so let's put a 42 here just for fun. There we go. See what happens. Let's get nuts.
That looks fun.
This is what we do on our.
Okay, so
Throw big numbers.
can you solve it? So guys, typically I talk about how to solve these like a week from now, but Michael has asked now, so here we are. And I mean, this is a good thing because before long I'll have covered all the material and I'll just have to like not have class the last 2 weeks, right? I shouldn't even say that out loud. If I say that out loud, you're going to expect me to do it.
It's too late.
And Michael, you would be upset if we didn't have class the last 2 weeks, right?
You would? Michael.
He's serious. Let's see here. Oh, we can just, all right, let's focus on this problem. Don't worry. There'll be plenty of math to fill the rest of the semester because you guys agreed that I can do calculus in the last week, right?
Wait, what? I don't think any of us consented to that.
As long as the calculus isn't anywhere in the final.
Oh, fine. I tried. All right, so any ideas? How do we solve this? Here's what you do. Use properties of the log to collect the logs together. So like here, this is the same as the natural log of x minus 2 times x plus 2 by the properties of the log, right? The sum property. And on the other side, you've got, well, natural log of 42. So I've talked some about how when you have an exponential equation, you take the log of both sides to solve it. We'll work another one of those soon, okay? But here, we've got a natural log equation. Well, guess what the natural enemy of the natural log equation is? It's the x. No, it doesn't. Logarithms don't phase it. That's just a log of a log, which is just uglier. But the natural enemy to the natural log is this. See, e to the natural log of stuff is equal to stuff.
No, and no.
Because exponential and natural log are inverse functions. Now the stuff has to be positive, all right? So there's that. But that's what we do. We just exponentiate both sides. So e to that is equal to e to that. And then that gives us x minus 2 times x plus 2 is equal to 42. At which point you wax nostalgic for week 2 in this course, right? Because this is a quadratic equation, which
Here's the joy.
we have solved hundreds of in here, I feel like.
So combine the parentheses together.
Oh, if by that you mean multiply it out,
Yes.
x squared minus 4 equals to 42, right?
What?
Because you get a minus 2x and a plus 2x, and they be canceling. Hey, can a ninja throw a throwing star?
Of course he would.
The correct answer is sure he can. That was a shuriken joke. There are those who are cultured and can understand this joke, and there's those who are not cultured and cannot understand this joke. When I think of well-rounded, I think of a proper dose of anime watching. Some people say reading Shakespeare or something. No, I say ingesting the Naruto, perhaps. Or, I'm sorry, Naruto. Don't want you to make you think I'm a brute or something. I'll tell you my favorite thing this semester. The favorite thing for me that's happened this entire semester is one of my students, one of my upperclassmen, in one of my higher level classes, he has a tattoo of one of the major, well, minor characters in Naruto, actually. What's his name? Shikamaru, right? Chicken what? No. Shikamaru? Now, I am saying that wrong because there's another student in this class who has said, as soon as he said it, he said, dude, you've got a tattoo of him, but you can't even say his name right. And then he proceeded to say Shikamaru in the correct, probably mostly correct Japanese way. And it gave me joy that I have both of these creatures in my class. All right, I digress. How do we solve that?
Square.
Let's get rid of that
Both sides.
Square root of both sides? So Michael gives me a square root of 46. Anyone care to add to that? Or take away?
6.78.
Maybe take away from it?
6.78.
I'm fishing for the plus minus that we're missing here. Yeah? Plus minus, right? Square root property. Two answers. Oh. Now, I shouldn't really put a box around that yet, right? Because this kind of problem, we actually, we need to check. We need to go back and check the original problem. So like natural log of the square root of 46 minus 2 plus the natural log 46 plus 2 is in fact
ln square root of 46.
Now, you don't actually have to go through the mechanics of checking the whole thing. All I'm really looking for here is that both of the natural logs are actually reasonable. So the square root of 46 is what? It's about like 6.5-ish? 6 point what? So this is positive, and this is positive. My point to you is that x equals to the square root of 46 makes sense for the original equation. So in fact, we can say x equals to x equal to the square root of 46 is a legit solution here. What about minus the square root of 46? What are you looking at then? Natural log of minus the square root of 46 minus 2.
Negative
And I can stop right there, by the way, guys.
minus 2 plus.
Do you see that? So both of these natural logs, they're natural log of a what? Of a negative number. These do not exist. As real numbers, at least.
It says domain error.
That's right. So in other words,
CN.
x equals to minus the square root of 46. This is an extraneous solution.
Oh.
It's extraneous. It doesn't count. It's not in the solution set. But the square root of 46 is. In the homework problem, it's like this, which was what? 107, was it? 109. It's much the same, I think. Any questions? Does that make sense? I think I'm supposed to talk about the graph of logs at some point in here. We haven't done that yet. We should probably do that, right? What does the graph of a logarithm look like? How do we graph? The logarithm is the inverse function to an exponential, right? So it's probably a good idea for us to graph both the exponential and the logarithm on the same graph to appreciate how they're related. All right? Are we done with this one? Can I erase the middle board? Everybody good? If not, just speak up. What's that?
Just watch on YouTube
Oh.
again if you missed it.
Unless
Well, I think I am my own worst cameraman, but I think I moved it.
you know someone at the back who just
I mean, I used to do that, but I get so many more steps in coming back here and back and forth, you know? Of course, I don't have the... I really should get one of those... I should get one of those watches that counts the steps. That way it would count. Because I don't have one of those, so... All my steps are wasted. All right, so... I used to have a watch that counts steps, and I used to go park at Walmart just so I could get a couple thousand steps, you know? Because my children just sit at home, and while they're studying, and they just, their hands down their side doing this. Because, you know, it counts. Let's see here. Cheaters. All right, graph. So this is the line y equals x. And the graph of the exponential, log base a, let's see here, it goes through something like that, right? So what does the graph of the logarithm have to look like? It should be the same shape, right, but reflected across the line y equals x. And for instance, here's something to notice. This point right here is what? It's 0, 1. And there's another point up here somewhere, say here, which would be 1a, right? And I guess there's another point like here, if I wanted to, I can include that in the story, minus 1 over a, right? There's 3 points on the graph of the exponential that we can study how those transform to be corresponding points on the graph of the inverse function, which we call the logarithm, right? So let's see here. We go to what? 1 over a minus 1, so that's like down here. And 0, 1 flips to what? 1, 0. And finally, 1a flips to a1. And so here's the graph of the logarithm, something like this. Oh, I'm sorry. I seem to be using this hideous Carolina blue again. My apologies. Let me write equations that correspond to the 3 points I just wrote in blue. What are the 3 equations you could write? The one equation I could write is like log base a of 1 over a equals to what? Log base a of 1 equals to what? Log base a of a equals to what? Fill in the blanks here. I'll get out of it. I'll give you a second to write it down, Michael. No need to stress.
Got it.
Okay, so what's the log base a of 1 over a equal to?
Log base of 1 over a is equal to log base of 1 over a negative -1.
Who votes for -1? All right. Who refuses to vote? Because votes don't mean anything. Okay, no, sorry. Too soon? Sorry. What am I saying? Votes are meaningful. Yeah, -1 is the right answer because that's a to the -1, right? So correspondingly, this point right here. See, log of 1 over a is -1. Log of 1, 0. And log base a of a is 1. That's the 3 points that I graphed, right? What else can we appreciate from this? How about this? The domain of the exponential is equal to the range of the logarithm, right? And what is it? I heard 0 to infinity. That's half of it. What's the domain of the exponential? A to the x makes sense for x what? For any x.
Negative infinity to infinity.
Yeah, negative infinity to infinity. Notice that the range of the logarithm does what? It goes down, 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 down. And it goes up, 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 up. So the range is everything for the logarithm. How about the range of the exponential? It's equal to the domain of the logarithm, right? And that is what you told me a second ago, 0 to infinity. That's the one. That's 0 to infinity. This is the key thing we must recognize now when we're thinking about finding the domain of new functions, is the domain. Now we've got 3 things to worry about when we think about the formula for a domain, right? First of all, we need to not divide by 0. Second of all, we need to make sure we don't take the square root of a negative number, right? But now third, we can't take the log of a negative number. Those are pretty much the 3 guidelines, the 3 things we think about when we're figuring out the domain for a formula in here. So example, oh man, 4? Was example 4? I don't know.
If we count that one as 4, then this one.
Well, this is a discussion. This isn't an example. This is, so 4 it is? All right, fine. So suppose you've got f of x is equal to the square root of 1 minus x plus the natural log of x minus 5, all divided by x minus 8. What's the domain? This has got everything in it, okay? So what are the 3 things you need for this formula to make sense? What's the domain of the function is my question.
3 things. Domain.
What do we need? We need
the switch.
1 minus x has to be greater than or equal to 0, right? We could take the square root of 0, that's fine, right? We're allowed to take the square root of 0. Square root of 0 is 0. We need, from this,
The natural log
we need x minus 5
is greater than 0.
greater than 0. Now there, I don't put equality. Why? Because the natural log of 0, like we were talking about earlier, is not defined. All right? And that never gets better. Like I don't define natural log of 0 in the complex analysis class, for example. And then, how about the denominator? That one's easier, right? X not equal to 8, right?
So now we do
And
Now, I just made this up. Is the domain anything? Or have I made a problem which is never makes sense? Let's find out. Because I wasn't thinking that hard when I wrote this down. There's a chance that this doesn't make sense for anything. Now, so this is what? 1 is greater than or equal to x, right? Agree? So if I draw that, if here's my number 1, so that one, basically over here, no wait a minute, my bad. X is what?
x is equal,
X is less than 1, right?
less than 1.
So like there's that x. So it's like this, right? Let me do the other one in red. So this says x is what? Greater than 5, right?
Greater than 5.
Oops. So that's over here. That's like this. So I can stop right there. The domain of this function is nothing. All right, so most people would say that this is not something you can do. This would be a very bad question to put on a test, for instance. All right. It's impossible to simultaneously have x to be less than 1 and x to be greater than 5. We can't have both of those at once, right? So, sorry, I kind of have to say, okay, so at this point I'd say that, well, the domain of f is empty, is the empty set. Let me fix this example. It's easy enough to fix, right? So example 5, what if instead of that I had f of x was like the square root of, let's say, x minus 1 plus the natural log of x minus 5 all divided by x minus 8. Right? So almost the same thing, but now I need what? I need x.
X is greater
Great.
than or equal to 1.
X greater than.
X is greater than 5.
Mm-hmm.
X is not equal to 8.
Right. And can you guys sort through that? Like, we need all of those three things at once, right? For the formula to work, we need all three parts of it to be functioning. So then what? Well, I like to, yeah. Yeah? I thought you were going to say something. It's okay. So my number line, here's 1, here's 5, right? So we need x to be greater than or equal to 1. We need x to be greater than 5. And we need to remove 8 from the consideration, right? So you notice that like 1 is less than or equal, well, let's see here. 1 is less than 5, right? Anyway, my point to you is that if we have, let me say it this way, if we have x is greater than 5, then automatically, right? If x is greater than 5, it's automatically greater than or equal to 1, right? So what's the domain?
Wait a minute.
So we want 5 to where? I have to throw 8 out, right? So I remove 8, delete the 8.
8 to infinity.
Yep. So that's how that one would go. Oh, and I guess we're out of time. Have a good weekend, you guys.
And just in time because my formula sheet is completely full.
That's good, Michael.